You know, when I was young, I had a lot of friends who wanted to know, what good is math going to do me in life? I don't really see how I'm going to be able to apply this to anything. Well, without being too cynical, you may be asking the same thing right now about root locus. What good will root locus do me in this class, or in life, however you want to think about it? So to answer this, I want to look at a specific example. So I want to look at g of s as some 1 over s times s plus 2. So this is our plant. It's an unstable plant. And so in open loop, if we provide a reference input r of s to this plant g of s to get y of s, g of s stability is something that we can analyze. So it's definitely not stable because we have a pole at s equals to 0. So will feedback make this plant stable? That is, can I stabilize the system with feedback? I want to put a k right here and see whether the system is going to obey me, do what I want it to do, however you want to think about this. So in order to make this happen, I'm going to choose just a controller equal to k. And so my closed loop transfer function h of s will be g over 1 plus k times g, or 1 over delta s. So my delta s characteristic equation is s squared plus 2s plus k. And if this is the case, then I'm stable for k greater than 0. So anything greater than 0 is going to give me stability. So I know this by looking at just the characteristic equation. But I want to know, for example, can I pick k such that I get a settling time less than 5 seconds and percent overshoot less than some percentage? So now I'm not just worried about stability, but I'm worried about meeting design parameters. This is where the root locus will help me. So again, our open loop transfer function g, which is the transfer function of the plant, is 1 over s times s plus 2. So if I plot this in the frequency domain, the s domain, I have a pole at 0 and a pole at minus 2. So first I'm going to draw the pole 0 map. Then I'm going to draw the real axis points. And next I'm going to calculate the location of the centroid of the asymptotes and the angles of the asymptotes. So the centroid of the asymptotes is the sum of the value of the poles minus the zeros, divided by the number of poles minus the number of zeros. So the center of the asymptotes is at minus 1, so I'll indicate that on the map here. The angles, because we have 2 more poles than zeros, turn out to be plus and minus 90 degrees. So the more examples you'll see, the more this is going to make sense. So 90 degrees and 270 degrees. So my asymptote's basically going to be going straight up and down from top to bottom at minus 1. So I could calculate the j omega crossing, but actually this system doesn't cross the j omega axis because there's no marginal stability for the closed loop system. That is, when we start with k equals 0, our system is unstable, but for any value greater than k equals to 0, we don't have any elements of the left-hand column that are equal to 0. So we don't have marginal stability. So we can calculate the breakaway point. In order to do that, we create this magical function p of s, which is the inverse of GOL of s, set it equal to 0 and take the derivative, find the maximum value at s equals minus 1. So, this is where we expected the breakaway to be, right here on the asymptote. So the angles of departure and arrival don't really matter for this example. So we can see that as we turn up the heat, the gain k, that our 2 poles come together, one from the left, one from the right, and then one heads up and the other heads down. So how do we use this to find k? We know how to plot the root locus. How do I find the k to meet these design constraints? So if I have the goal of having percent overshoot be less than a certain value, it means that that's going to translate into zeta being greater than a certain value, because zeta tells me about damping. And so I'm going to pick a value zeta somewhere along this curve, zeta being 1 here on the real axis and zeta being 0 here on the imaginary axis. So I'm going to pick some value of zeta that's going to provide this performance constraint for percent overshoot. So if I take a couple of logs here to make life easier for me, so now I can divide through by minus pi and get 1 minus zeta squared square root equals zeta. Do a couple of squares, add a couple of numbers, take a couple of square roots, and we get zeta equals to 0.707, or 1 over the square root of 2. So this value of zeta will satisfy my percent overshoot requirement. And with this value of zeta, we know what our angle needs to be. So the arc sine of 0.707 tells me that zeta is going to be that the angle is going to be 45 degrees here. So anywhere inside of this region is going to give me happiness. So as zeta tends to 0, I'll have more oscillation. As zeta tends to 1, I'll have more damping.
So with this value of zeta, I can now go ahead and calculate the omega n requirement based on what zeta has to be. So in this case, if we substitute zeta equals 0.707, we calculate omega n must be greater than 1.1315. So now we can go ahead and plot what this looks like on the root locus. So in this case, we know that omega n must be greater than some radius, and I've sort of sketched that radius here. And now we can look at regions of the plot, regions of the root locus that satisfy our pole requirements. So that's this region here in yellow. So anything in yellow will basically allow us to meet the settling time requirement and percent overshoot requirements that we have. Anything that's out here in the red violates the zeta requirements. The parts that are in here satisfy zeta, but they don't satisfy the settling time requirement for omega n. And these two parts don't satisfy any one. So now we can check to see whether a specific value is going to work. So if we look at the particular plot, we see that in this area right here, that it's really close. So we can't tell whether the root locus actually passes through the points that allow us to have a correct plot, right? So not a correct plot, but a good controller. So we want our controller to have these capabilities, but our controller is limited to only be on the root locus. And so if the root locus passes inside that blue circle, the blue half circle, and goes through the lines defined by zeta before it gets out of the blue circle, then we'll be unhappy. So I'm just going to pick this point right here, and I know what it is because this value, we know that zeta was equal to 0.707, which is 45 degrees. We know this is J1 and that this is minus 1. And so over here I've gone ahead and drawn the pole S equals minus 1 plus J1. And now I can use the fact that we know zeta and omega n for these complex poles to make up the real and then the imaginary parts. So the real part minus zeta omega n is going to be minus 1, and the imaginary part omega n times square root of 1 minus zeta squared is also 1. So now it's just a matter of substituting in the value of zeta that we have, minus 0.707, and solving that omega n would be equal to 1.414. So since that value is greater than what we say omega n has to be here, we know that there is at least some range of k. It may be fairly small that will work, that will give us the controller specifications that we'd like to have.